Hello! Today we are going to look at the motion of a projectile thrown into the Earth's gravitational field. Let's see how such motion is described and what principles we can use to then solve a problem on this topic. Let me remind you that when we throw a body into the Earth's gravitational field, we call this motion also free fall. That is, only one force acts on the body. It is the force of gravity, and it gives the body at any point of its trajectory the same acceleration. This is the acceleration of free fall. I will also remind you that in cases of such motion, we will neglect air resistance. That is, we consider the ideal case when this motion is not hindered by anything. Therefore, we will immediately note for ourselves 2 points which in fact we will have to take into account. That is, in this case, we neglect air resistance, and the acceleration that this body has is determined by the acceleration of free fall. And its numerical value we know, of course, too. These are the two factors we will use to describe the motion of any body that is thrown into the Earth's gravitational field. The first principle that is used in this motion is called the principle of independence of motion. That is, we can break down the motion of a given body that participates simultaneously in flight and moves along the x-axis or along the y-axis into two independent components. Let's look at this using the example of a wagon that is moving along a horizontal surface. And let's say an apple falls from its window. The apple is initially at this point. When the wagon moves forward with some speed, it has a speed, which we will denote v1. And the same speed has all objects inside the wagon, including the apple. And for the person who's in that carriage. And observing the apple, he will see that the apple is just falling down vertically without seeing that there's any other horizontal movement. What will a person who is on the ground and watching this apple relative to the ground see? He's going to see that this carriage is moving horizontally, and the apple is also moving horizontally. So the apple has a trajectory like this of falling. There are two components of motion, i.e., it has moved this object along the y-axis, and it has also moved along the x-axis. These two components of motion, which in this case arise, we can consider independently of each other, describing them by appropriate equations. Let's remember how motion is described for each of these components, and let's see what the final equation to describe such motion looks like. First, let's take the motion along the x-axis, and here we see that there are no forces along this direction, so accordingly there are no accelerations. We have only one acceleration. It is the acceleration of free fall, and it is directed vertically downwards. Let's apply the equation of uniform motion along the x-axis and solve the equation for the value of the final coordinate along this axis. So, the final coordinate is the initial coordinate plus product of the velocity of the body by the time of motion. In this case, the velocity along the x-axis, of course. That is the velocity that was moving into this car. In this situation, accordingly, the apple had that same velocity. As for the y-axis, in this case, the final y-axis coordinate will be determined by the sum of the initial y-axis coordinate, further the initial y-axis velocity. Times time plus the y acceleration times t squared divided by 2. This is our coordinate equation for equal acceleration. Now our task is to adapt these coordinates a little bit for a more simplified perception of this information. For this purpose, we can take the starting point as the origin, i.e., where we started to consider the motion. Accordingly, we can take the x-axis coordinate as 0, and then for the x-axis coordinate, we will get the value of the final coordinate as simply the product of the x-axis velocity multiplied by time. For simplicity, we can remove the value of the initial coordinate in this way by combining its value with the origin of motion. And we get the value for the y-axis coordinate in the same way. That is, we know the initial coordinate. Then, the velocity along the y-axis, here some may be initial, may not be. That is, depending on how this object moves, we will generally set it aside here, because again we will consider different situations in the future. And the acceleration that this object has, in this case, is directed against the positive y direction. And then we get the value of minus gt squared divided by 2. This is how we get a system of two equations which, solving together, we can already consider problems of different types. We can also consider what form the given trajectory has. For simplicity, we can consider the case when some object is thrown horizontally from some tower with an initial velocity. And then we realize that this object will travel along the y-axis and along the x-axis until it falls to the ground. The velocity in this case has a direction oblique to this trajectory at each point, and also respectively has two components. On the y-axis and on the x-axis. And here we see that the velocity along the x-axis will always be conserved. So this component, we have this constant value, but the velocity along the y-axis will increase as the body falls. We can also write the law of velocity. So we can say that the initial velocity is a constant, but the y-axis velocity is the initial y-axis velocity plus gt. And then we consider different situations depending on how the body was thrown. The trajectory along which this body will move, in this case, is a parabola. And this can be investigated if we solve these two equations together, that is, by getting rid of time. And after calculations and derivation of equations, we will be convinced that the trajectory of such motion is a parabola, which is inverted with branches downwards. That concludes our lesson. We'll see you in the next lesson. Goodbye.